We will first briefly introduce the concept and then go to details about biochemical reactions, microorganisms, biochemistry, as well as the operation conditions. First, let's see the distinction between conventional heterotrophic denitrification and the emerging field of autotrophic denitrification, particularly sulfur-driven autotrophic denitrifications. Heterotrophic denitrification is widely used in wastewater treatment and relies on organic matter as the electron donor. It is effective. However, it also has several challenges associated with this conventional method. The use of organic matter leads to higher sludge production compared to other methods. This not only poses challenge in sludge management, but also increase the operational costs significantly. Another concern is the increase in residue organics in the treated effluents. The presence of these organics can be problematic, especially as they may require further treatment steps before the effluent can be considered safe for discharge or reuse. In contrast, the past decades has already a growing interest in autotrophic denitrification processes, which do not rely on organic carbon source as electron donor. Among those autotrophic denitrification, sulfur-driven autotrophic denitrification has also gained particular attention. Sulfur-driven autotrophic denitrification uses inorganic compounds such as sulfur as the electron donor. This shift from organic to inorganic electron donors can significantly reduce sludge production and lower the presence of residue organics in the effluent. By minimizing sludge production and additional treatment requirements for residue organics, sulfide-driven autotrophic denitrification can potentially lower operational costs, making it a more cost-effective option in the long run. The reduced sludge and the lower organic residue contribute to a smaller environment footprint, aligning with more sustainable wastewater treatment practice. Now let's dive deeper into the advantages of sulfur-driven autotrophic denitrification process. Unlike traditional heterotrophic denitrification, sulfur-driven autotrophic denitrification does not require external organic carbon source. Then this is significant benefits as it eliminates the need to add costly organic compounds. At the meantime, it also do not contribute to the problem of residue organics, since it does not rely on organic carbon, leading to cleaner effluents. Sulfur autotrophic denitrification also have a significant lower biomass yield coefficient. For every gram of nitrate denitrified, sulfur denitrification produces between 0.15 to 0.57 grams of autotrophic biomass, while heterotrophic process produce 0.71 to up to 1.2 grams of heterotrophic biomass. This reduced the biomass production significantly. Another environmental advantage is sulfur denitrification can reduce nitrous oxide emission. When sufficient sulfur is available, there will be significant reduction in nitrous oxide accumulation and emission during the denitrification process. Sulfur-driven autotrophic denitrification is a cost-effective, innovative technology for handling carbon-deficient, sulfur-laden wastewater across various industries. For example, landfill leachate often contains high level of sulfur and low level of biodegradable organic carbon. Sulfur denitrification can efficiently reduce nitrogen content, making the process more straightforward and cost-effective. Well, in aquaculture systems, managing the nitrogen cycle is crucial. Sulfur denitrification offers a robust solution to remove nitrates effectively, ensuring the health of aquatic life and the sustainability of the aquaculture environment. And wastewater from the petrochemical industry can be challenging due to their complex composition. Sulfur denitrification's ability makes it ideal for treating these types of wastewater, reducing both complexity and cost. Following anaerobic treatment, effluents may still contain undesirable levels of nitrates. Sulfur denitrification provides an effective polishing step, enhance the overall treatment efficiency. One more example, like during biogas production, hydrogen sulfide must be removed to prevent corrosion and to meet quality standards for energy use. Sulfur denitrification not only aids in desulfurization, but also in the simultaneous removal of nitrates. Moreover, sulfur denitrification can also play a critical role in preventing the corrosion commonly caused by sulfuric acids in sewer system, aiding lifespan and reliability to civil infrastructure. After overview of the concepts, let's see some details about the biochemical reaction. First, let's see the transformations and energy implications of sulfur oxidation and nitrogen oxide reduction reactions, particularly in bioremediation wastewater treatment context. The oxidation of sulfide is crucial in many environmental and industrial processes, involving the transfer of 8 electrons from sulfide sulfur to oxygen, converting it to sulfate. This reaction is not merely of chemical interest, but is also highly energetically favorable for chemoautotrophs, providing essential energy for their metabolic activities. Using nitrogen oxides as the electron acceptor for sulfide oxidation is especially beneficial, as shown by the standard Gibbs free energy changes in the equation of 7.7 and 7.8 from the textbook. The intermediate formation of elemental sulfur is also well known. Research indicates that the formation is highly dependent on sulfide concentration when nitrate serves as electron acceptor. Converting sulfide to biogenic elemental sulfur requires 4 times less nitrogen oxide than fully oxidize it to sulfate, making it a preferred pathway under limited electron acceptor conditions. In such scenarios, oxidizing excess sulfide is advantageous due to its greater bioavailability to denitrifiers compared to accumulated biogenic elemental sulfur. Moreover, energetically reduced nitrite is more favorable than reducing nitrate, as reflected by the more negative standard Gibbs free energy changes in equation 7.11 and 7.12. It is important to note that the actual consumption of sulfur compounds often surpass stoichiometry values, largely due to the cell growth of sulfur-oxidizing bacteria, because these bacteria utilize sulfur compounds for both energy production and also biomass construction, increasing overall consumption, which might be about 30 to 38% of higher. The stoichiometric biochemical reactions of complete denitrification, particularly from nitrate using inorganic sources, are well established. These reactions account for biomass growth associated with anabolism, essential for a comprehensive understanding of the biochemical dynamics. These reactions can be referred to the equations 7.13 to 7.15 in the textbook. The efficiency of sulfur salts in the denitrification process can vary. For instance, using sulfide as electron donor, reducing 1 gram of nitrate nitrogen typically reduce 5.58 gram of sulfate. With chemical elemental sulfur, this yield will increase to 7.8 gram of sulfate. Well, if with cell sulfate, the reaction is most efficient, producing 11 gram of sulfate per gram of nitrogen reduced. Although it is efficient, sulfur-driven autotrophic denitrification technology faces limitations, particularly in treating ground and surface waters contaminated by nitrate and nitrite. The byproducts, primarily sulfate, can accumulate, potentially causing secondary contamination issues. These limitations are crucial in addressing the feasibility and environmental impact of sulfur autotrophic denitrification technology in water treatment. After review the biochemical reactions, let's also look at microorganisms in the sulfur-driven autotrophic denitrification process. The microbial consortia in the sulfur-driven autotrophic denitrification process are phylogenetically diverse, primarily comprising sulfur-oxidizing and nitrate-reducing bacteria. These bacteria predominantly belong to the phyla Proteobacteria, Firmicutes, Chlorophyllix, Chlorobin. The genera Bacillus, Salmonus, and Sulfur-monas are among the most recognized sulfur-oxidizing bacteria for autotrophic denitrification, deriving energy for both denitrification and biomass synthesis, mainly from sulfur oxidation. The composition and diversity of SOB vary considerably based on the type of electron donor used. The key genera such as Bacillus and Sulfur-monas, which function as obligate or facultative chemolysotrophs, have their optimal growth condition driven by different electron donors, detailed in the textbook Table 7.6. Facultative chemolithotrophs, sulfate-reducing bacteria, can grow either autotrophically or mixotrophically using complex organic carbon for both carbon and energy. To date, numerous sulfur-oxidizing bacteria species have been isolated from diverse environments such as sediments, hydrothermal vents, oceans, soda links, hypersaline lakes, with many playing a role in the sulfur-driven autotrophic denitrification. Textbook Table 7.7 details this SOB and their optimal growth conditions. SOB species exhibit growth across various pH levels. For instance, this cell microspira thrives in a pH range of 5.5 to 8.5, while cell bacillus denitrificans prefer neutral pH condition. Some SOB are acidophiles, flourish at a pH level below 5.0, whereas others like Cyalcavibrio nitroridens and cell bacillus versatus only grow in alkali condition. And most SOB have an optimal growth temperature around 30 degrees Celsius, though some, such as Pyrococcus, tolerate both psychrophilic and thermophilic conditions. In addition, the composition of microbial community can be significantly influenced by changes in operational parameters, such as initial sulfur and nitrate concentrations, reactor temperature, pH, hydraulic retention time. The choice of electron-donating substrate also play a crucial role in shaping microbial community structure. For example, Chlorobaculum, cell bacillus, Sulfurimonus are the dominant genera in a cell sulfate-driven, sulfur-driven autotrophic denitrification system, whereas Acetobacter, cell bacillus, and cell thrax are more prevalent in a sulfide-driven SDAD process. Some genera in low relative abundance can change to a higher relative abundance depending on the type of electron donor. For instance, Terra has much higher relative abundance in a chemical sulfur-based, sulfur-driven autotrophic denitrification system than that in a cell sulfate-based, sulfur-driven autotrophic denitrification system. Moreover, different functional microorganisms can be enriched respectively at a low, medium, or high sulfide loading rate, which is an important factor affecting the microbial communities in a simultaneous desulfurization and denitrification process. Next part, let's look at biochemistry for sulfur-driven autotrophic denitrification process. Sulfide, chemical sulfur, cell sulfate are the most common electrodonors for SOB, with their metabolic pathway and fundamental enzymes detailed in textbook Figure 7.6. The key pathways identified include the first one, the SOX-independent pathway, utilizing unique oxidase and hydrolase for oxidation of sulfide, sulfur chemical sulfur, and cell sulfate. Secondly, the tetracyanate pathway for cell sulfate oxidation are also shown in figure 7.6. And the third pathway is SOX-dependent enzymatic pathway. The sulfide oxidation begins with the sulfide quinol oxidoreductase, SQR in short. So a flavor protein essential in both photo and chemical lysotrophic bacteria. So this is SQR enzyme. An alternative enzyme, which is flavor cytochrome C sulfide dehydrogenase, in short we call FCSD, operates similarly in the periplasma. SQR initial reaction product soluble polysulfide spontaneously convert into biological sulfur globules. These sulfur globules, formed periplasmatically, are transported into the cytoplasm by a sulfur carrier enzymatic system, SCS, and oxidized to sulfide by DSR enzyme. The oxidation of sulfate involves either the sulfide oxidize, transforming electrons to cytochrome C, or sulfur chemolysotrophs, or using APS reductase in reverse activity. Cell sulfate oxidation can occur through a SOX-independent enzyme system that initially forms tetracyanate via cell sulfate quinol oxidoreductase, followed by its conversion to sulfate through hydrolysis by cytoplasmic polycyanide hydrolysis. This pathway involving polycyanate formation is prevalent among several beta and gamma proteobacteria, particularly in obligate chemolysotrophic like acidocyanobacillus. The SOX-dependent enzyme complex, known as the SOX alpha proteobacteria multiple enzyme complex, operates under a conserved SOX operation. The SOX SYJABCD gene cluster encodes the components of the sulfur oxidizing system, producing 4 proteins, which are SOXXA, SOXYJ, SOXB, and SOXCD, necessarily for sulfur-dependent cytochrome C reduction. This complex efficiently oxidizes various sulfur substrates, such as sulfide, cell sulfate, and sulfur elemental, into sulfate. For more detailed information on sulfur oxidation pathway and enzymes, please refer to our textbook. Biological autotrophic denitrification involves 4 microbial nitrogen reductive reactions: dissimilatory nitrate reduction, nitride reduction, nitric acid reduction, and nitrous oxide reduction. These reactions are driven by complex multi-site metalloenzymes, requires 10 more of electrons and 12 more of hydrogen to reduce 1 more of nitrate to nitrogen gas. The process begins with the reduction of nitrate to nitride by a molybdenum containing nitrate reductase, NAR, located either in the cytoplasm, NARGH, or in the periplasm, NAPAB. So nitride is then reduced to nitric acid by periplasmic nitride reductase, and subsequently nitric oxide is converted to nitrous oxide and water by a membrane-bound nitric oxide reductase, NOR, which containing Hemi C, Hemi B, and non-Hemi iron. And the final step involves the reduction of nitrous oxide to dinitrogen gas by a copper-containing nitrous oxide reductase, NOS. And for sulfur-driven autotrophic denitrification process, the electron distribution and the compactation in this sulfur process are very important. So here you can see the electron distribution pathway in the sulfur denitrification process is shown in textbook figure 7.7. Dissolved sulfide can be converted into biological sulfur elemental by the SQR enzyme, or into SO4 sulfate by the SOX enzyme complex. The electrons generated from the oxidation of inorganic sulfur electron donors facilitate the membrane-bound NAR to perform nitrate reduction to nitride. On the other hand, the compactation between different nitrogen oxide reductases, such as NAR, NIR, NOR, and NOS, as mentioned in previous slide, commonly exists in the respiratory chain of denitrification. Compete for electrons among NAR, NIR, NOR, and NOS regulates the electron distribution among the denitrification steps and determines the possible accumulation of nitrogen compounds. And if we link sulfur cycle and the nitrogen cycle together, we can find sulfur substrate can possess different oxidation rates and subsequent electron flows in the electron transport chain. An electron compactation among the nitrogen oxide reductase affect the reduction rates of the nitrogen oxides and to be responsible for accumulation of the intermediates, such as nitride and nitrous oxide. After introducing the fundamentals, let's look at some examples and operational conditions governing the sulfur-driven autotrophic denitrification process. Firstly, chemical sulfur elemental is a commonly used electron donor in sulfur denitrification process, since it is cost-effective, easily available, and less toxic compared with other sulfur substrate. Sulfur limestone typically offers a dual source of chemical sulfur and alkalinity for sulfur denitrification application, and enables SOB-enriched biofilm to develop on the sulfur particles packed in a bioreactor. However, the major drawbacks of chemical sulfur is its low aqueous solubility and its low mass transfer rate in the reactor, thus impeding the electron transportation and autotrophic denitrification. Hence, a biofilm reactor with chemical sulfur as a carrier is often recommended for improving the mass transfer efficiency of the reactor. Compared with chemical sulfur elemental, the biological elemental sulfur is more reactive and bioavailable for autotrophic microorganisms, owing to the also hombic structure of sulfur crystal covered by a hydrophilic layer of neutral-charged polymers. Sulfide, of course, also has been employed as an electron donor, but we have to pay attention. The sulfide is toxic to SOB when its concentration exceeds 200 mg sulfur per liter. It will affect the NAR activity, and some method to control this toxicity is important. Another sulfur source is cell sulfate, present in some industrial elements, acts as the most effective sulfur substrate for SDAD and least inhibitory to SOB, whose tolerance can be up to 2000 mg sulfur per liter, which is 10 times greater than that of sulfide. However, the instability of cell sulfate, as it will readily decompose, this instability may limit its application as an electron donor source. For a large-scale engineering application, selection of most suitable substrate should be based on kinetic cost and availability to microorganisms. On the other hand, nitrogen oxide is also important. We use the sulfur-nitrogen mass ratio to correlate it with the nitrogen and the sulfur reactions. When sulfur and the nitrogen mass ratio is close to 2.1 gram sulfur per gram nitrogen, it starts significantly reducing the emission of nitrous oxide. At a low sulfur to nitrogen mass ratio, the lack of an electron source can lead to accumulation of nitrite, which inhibits denitrification. A higher sulfur to nitrogen mass ratio favors biological sulfur elemental as the main final products, while sulfate is a preferential product of sulfide oxidation, accompanied by complete denitrification. When the sulfur to nitrogen mass ratio is below the stoichiometric value, which is 1.4 gram sulfur per gram nitrogen. And if there is a minimum sulfur-nitrogen mass ratio of at 1.6 gram sulfur per gram nitrogen, it could achieve 90% of nitrate removal, which is higher than the theoretical 1.4 gram sulfur per gram nitrogen. It is because of certain sulfur should be utilized for biomass growth. So regarding the biomass, there are also different type of biomass growth system, like activity sludge, biofilms, and granulars, which has been achieved in different bioreactor configurations, such as upper flow anaerobic sludge bed, biofilm reactor, packed bed biofilm reactor, moving bed biofilm reactor, significantly influence the biomass concentration and the reaction rate. It is important to maintain high biomass to improve the sulfur denitrification rate. Biofilm reactor is proven to be robust to perform well in sulfur denitrification. Packed bed reactor is particularly suitable for nitrate removal at a low concentration, since a long retention time, for example, larger than 3 hours, is required for complete denitrification. While moving bed biofilm reactor is suitable for maintaining high biomass content of slow-growing SOB, even under severe nitrate limitation condition, the MBBR still can achieve complete nitrate removal and it with a high resilience. Another method to improve the performance of sulfur denitrification is to granulate the isoB, which can facilitate both high biomass concentration and robustness for efficient and stable autotrophic denitrification. So all those details are for different bioreactor configurations and their applications in SDAD process. Please refer to textbook table 7.8. The key to successfully apply this technology is to attain sufficient slow grow SOB communities in the reactor. In addition, the operational conditions are also important for sulfur denitrification process. For example, the ratio of alkalinity to remove the nitrogen should be kept at approximately 4 to 4.5 milligram calcium carbonate per milligram nitrogen removed to correspond to the SOB optimal pH range of 6 to 8. Secondly, the dissolved oxygen concentration will also affect the growth of autotrophic denitrifier. Once the DO concentration is between 0.1 to 0.3 milligram oxygen per liter, there are already some inhibition on NOS activities. Well, if there is a oxygen concentration larger than 1.6 milligram per liter, there will be completely inhibition for sulfur-driven autotrophic denitrification. Regarding the temperature, so for most autotrophic denitrifiers, the suitable temperature range is generally 25 to 35 degrees C, and the sulfur-driven autotrophic denitrification process with sulfide as the electron donor, which can achieve the highest denitrification efficiency at 35 degrees Celsius. However, it will decrease to 36 to 60% when the temperature decreases to 15 degrees Celsius.